Welcome back, everyone. Today we're going to talk about Part B of Week 1. Specifically, we're going to be talking about numeral systems. So this is different systems in which you can represent or write down numbers. We'll specifically be looking at decimal, binary, octal, and hexadecimal numbers. That said, let's do a little quick review. So this is material from Part A of this week. Any piece of data that you store in your program or any piece of data on a computer has to be stored as a binary number. And remember, we talked about how if it's a numerical type, you convert that numerical type straight up to a binary number. That's what we're going to talk about today. If it's a string, you have to go through every single character, convert that character to a number using ASCII, and then convert that number into a binary number. So again, today the focus is going to be on how exactly we do these conversions to binary. Alright, before we get there, I want to do a quick review about decimal numbers. So these are numbers like we've grown up with numbers. These are numbers that are base 10. That's what the deci stands for in decimal. And the real only reason why we represent numbers the way we do in base 10 is because most humans have 10 fingers. If we had 8 fingers, we would be using base 8 with our numbers. If we had 5 fingers, we'd be using base 5, and so on. So really, the only reason we represent and write down numbers the way that we do is because we have 10 fingers, and it's very convenient for us to use base 10 numbers. Alright, so let's go back to kindergarten when we were first learning our numbers. Alright, so think about the number 142, right? Just the normal 142 that we're all used to. So if we broke down this number into the different places, there's the hundreds place, the tens place, and the ones place, right? This is where that base 10 system comes from. The hundreds place, also known as 10 to the power of 2, we have a 1 in it. In the tens place, 10 to the power of 1, we have a 4, meaning we have 4 tens in this number. And in the ones place, 10 to the power of 0, we have a 2, meaning there's 2 ones. So if I were going to write this number based on its places, it could look like this. Here we'll have a box for all of its places. This will be the ones, this will be the tens, this will be the hundred spot. And again, we're getting these numbers because everything's base 10. So the ones place is because 10 to the 0 is 1. The tens place, 10 to the 1 is 10. Hundreds place, 10 squared is 100. So to write this number 142 in base 10, we simply write down how many hundreds, how many tens, and how many ones. Like this. There's 1 hundreds, 4 tens, and 2 ones. That's 142 in decimal. Keeping that in mind, let's now talk about binary numbers. Alright, so again, when a computer thinks of a number, it's usually in base 2, binary. So this is another way to represent the same numbers that we're all used to, except instead of doing base 10, we're going to do base 2 now. So let's talk about then how we can convert from decimal to binary. Alright, so let's talk about the decimal number 11. So let's go back to this little diagram again. So if we have the number 11, in base 10, meaning the normal 11 that we're used to, we'll say this part right here, up here, This will be base 10. Down here we'll look at base 2. Alright, so we're looking at the decimal number 11. So this is the number that has 1 10 and 1 ones. Alright, so to convert from base 10 to base 2, we're going to do this same little place diagram again, except this time the places are all going to be base 2 instead of base 10. So this first place here is going to be 2 to the 0, which is the 1s. This place right here is going to be 2 to the 1, which is the 2s. Here we'll have 2 squared, which is the 4s. Here we'll have 2 cubed, which is the 8s. And here we'll have 2 to the 4th, which is the 16s. Alright, so these numbers 1, 2, 4, 8, 16, these are powers of 2. Just like how in base 10, these places, the 1s, the 10s, the 100s, those are all base 10. Alright, so again, we're converting this base 10 number 11 into base 2. And we do it the same way. We start with the largest base possible. So we start over here on the left. And again, we have the number 11, right? Now, 16, that's too big for 11, right? So we can't put anything in the 16 spot. So we move down. Now we look at 8. Okay, we can fit 1 8 into 11, right? We have the number 11, and we can fit an 8 into it. How many do we have left over after we deal with that 8? 11 minus 8, that's 3. So that means we still have 3 numbers left to deal with. Let's go to the 4 spot. We can't fit 4 into 3, right? There are no 4s left in 3. So that's going to be 0. Let's get to the 2. Okay, we can put a 2 into 3, right? We can fit 1 2 into 3. Cool, so we'll put a 1 there. We'll subtract off this 2 that we just dealt with, which means we have 1 left over, which is perfect, right? Because the next place is the 1s. So we'll go ahead and write a 1 there. So that means the decimal number 11 is the binary number, or rather the base 2 number, 1011. And that's it. That's how you convert between binary numbers, that's how you convert from a decimal number to a binary number. That's it. It's still the same number 11 that we're used to. It's just written in a different way, in a way such that every single digit is either a 0 or a 1. Let's do another example. Alright, so let's look at the number 15. Alright, so again, this is base 10, number 15. So let me go ahead and erase this stuff. And we're going to convert it to a base 2 number. Alright, so we can start off with the same sort of place setup. I might go ahead and extend this just a little bit to account for potentially larger numbers. Alright, so the next base 2 place is going to be what? 2 to the 5th, right? Which is 32. So that's going to be the 32nd place. Alright, so again, here we are going to convert the base 10 number 15 into base 2. Alright, so let's do that. So first thing we do, again, we start on the left-hand side of these base 2 places and we find the biggest one. That will go into 15. Alright, 32, nope, too big. 16, still too big. Alright, how about 8? Yes, we can fit 1 8 into 15, right? With 7 left over. So we'll put a 1 right there in the 8's place. Alright, cool. Let's keep moving to the right. Next spot is the 4s. And we have 7 left over that we're dealing with. Alright, well, yes, we can fit a 4 into 7. So we'll put a 1 there, subtract by 4, which means we have 3 left over. We can fit a 2 into 3, so we'll put a 1 in the 2 spot, subtract by 2, see how much we still have left. We have 1 left, perfect, put it right here, and we're done. So, 15, the decimal number 15, base 10 15, is 1111 when written in base 2, or in binary. It's not too bad, right? It's just writing that little places table, knowing your powers of 2, and doing a little bit of subtraction. That's it. Alright, so something to keep in mind, obviously, is the larger the number is, the more base 2 positions you need to know, right? And I've shown you 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 5th is 32, and so on. So do keep that in mind while you're working through these problems. The more places you need to deal with, the more powers of 2 you need to know. Alright, let's go ahead and talk about the algorithm then, right? Whenever we're talking about computer programs, we want to think about the algorithm behind what's going on, sort of the step-by-step instructions of what is happening. So here's a potential outline for an algorithm. I would challenge you to make this outline slightly better, meaning make it more explicit, make it more understandable, and so on. But we'll start with this algorithm. So this again is the algorithm for converting from a base 10 decimal number to a base 2 binary number. So first, you find the largest power of 2 that's either equal to or less than the number, right? And that's what we were doing with that little table we drew. We'd go as far to the left as possible and find the largest place that we could fit into the number. Once you find that spot, mark it with a 1, right? Because again, the digits, it's either 0 or 1. That's it. There's no other digits in base 2. So you got a 50-50 shot for every place, right? It's either 0 or 1. Mark that place with a 1. Subtract that power of 2 from the number, right? We were doing that sort of side work. Once we put in a 1, we did a subtraction to see how much we still had left over. And then you repeat this process, going down all the places until you have nothing left over. And then any place where you didn't put a 1, you're going to put a 0. Right, so this is essentially the step-by-step algorithm of what we just did in those last couple of examples. And when you are developing your own algorithms, this is sort of a good way to do it. Do a couple examples on paper by hand, and then think back to the process you followed, and then write down an outline of that process, but keep it general, right? So it'll work with basically any example. That said, let's go ahead and do one more example. So this one, I want to challenge you to do it on your own. So go ahead, grab a piece of paper, do what we were just doing, and I want you to find the binary representation, so the way to write this number in base 2, of the decimal number 50. So 50 is in base 10, and I want you to figure out what the base 2 representation is. Go ahead and pause this video and come back when you're done. Alright, so hopefully by now you've worked this out and you've gotten something like this, right? So again, going by those places, the largest power of 2 that fits into 50 is 32. That's 2 to the 5th. So we'll put a 1 in that first spot there. When you do the subtraction, 50 minus 32, you have 18 left over to deal with. Next power of 2 that fits into 18 is 16. Do that subtraction. 18 minus 16, 2 left over. So you go down a couple spots, right? Because the next power of 2 is 8. That's not going to work. 8 is way too big for 2. Next one is 4. Still too big. Next one is 2. That's perfect, right? We have 2. Next spot is 2. Cool. So you put a 1 in the 2 spot. then you have nothing left over, which means you put a 0 in the 1 spot. So the binary representation of the decimal number 50 is 110010. If you have any questions about this example, feel free to post to the discussion forum or send me a message in Canvas.